Hello everyone, today let's just take a look at QP 106, just proving some more things about expected value. So we have x and y that are discrete random variables on a probability space, and we have g that is any real valued function. And in part A, we need to show Lotus, which is the law of the unconscious statistician. I'm not sure why it's called that, but basically it is that the expected value of some function of a random variable x is just equal to all the values that that function can take times the probability of x occurring. This one's actually pretty simple to think about. If we have a random variable x on our probability space, well, that means that it assigns every single possible outcome in that probability space to some number. So it's basically going to partition our set. So maybe over here, x is assigned to the value of 1. And then maybe over here, x might be assigned the value of 5. Maybe over here, this is just an example, x might be assigned the value 2. So you can see x fully partitions our sample space. So now we take some function of that random variable x, let's just call it z, and let's say it's equal to g of x. And a function obviously takes every single value that x can take and it assigns it to some new value. So if g of x is equal to 2x, well then this one would be assigned to 4, this one would be assigned to 5 times 2, 10, this one would be assigned to 2, right? So in more general terms, we have a bunch of probability mass. X is a discrete random variable, so it takes some probability mass and assigns it a value like so. And then our function g of x takes all of these values that x can take and it assigns it a new value. So let's say that this is g of x1 and maybe it gets assigned to something, let's say z1. Now it does the same thing for x2. It just assigns it some new value. We take it and we assign it to maybe z2. And the definition of a function is that every single value in the domain, so x1 all the way up to xn, gets assigned some value in the codomain. So maybe xn gets assigned to zn, but a function does not have to be 1 to 1, right? So x2 could theoretically get assigned the same value that x1 did. So it would be g of x2 would also be equal to z1. And then if that happened, we would not have n different z values. We would have m, where m would be less than n. So now when we're taking the expected value of this function of x, obviously we know the definition of expected value. It's just going to be all the possible terms that the function of x can take, right? We're calling it z. So all the z in a big Z such that we take that value and we multiply it by the probability of occurrence. So now what's the probability of a specific z value occurring? Let's do that first. Well, if we take a specific z value, let's say z1, well then the probability of it occurring is just going to be equal to the union of basically all the probability mass that was assigned to it through this function. So more formally, what we can say is this is equal to the union over all of the values x prime, such that when we take that function of x prime, it's equal to the specific z value that we're trying to find the probability of. And then inside the union, we're taking the probability that x is equal to that x prime. So for instance, in our example with z1, we are taking x1, which is our first x prime, because that gets assigned a value of z1 through this function, and also x2 because it also gets assigned the same value of z1 through the same function. And then the probability that x is equal to each of these would be this probability mass over here. So now to find the union of a bunch of sets, we just use inclusion-exclusion, but since x fully partitions our sample space because it's a discrete random variable, we're going to have no intersection terms, so that we can just say that this is just equal to the sum over all the x prime in g of x prime equal to z times the probability that x is equal to x prime. That's the probability of z equaling some specific z value. So now let's just plug that in back to our original equation. And when we do that, it's going to look like this. And now since z is constant with respect to the iterator in here, we can just pull z inside of here and we will have something like this. So now we're summing up over all the possible values that z can take. And for each one of these different z values, we're taking all of the possible x values that got assigned to that z value. And since we know g is a function, that means that every single x got assigned to exactly one z value. So therefore, in this double summation right here, all we're doing is we're just summing up over every single possible x value. So we can replace that double sum with a single sum over all the possible values that x prime could take. So x prime in x, it's just going to be x prime because we were just using that as a dummy variable, but it's no different than x. And then z times the probability that x is equal to that x prime. And again, that x prime was a dummy variable. It's no different than if we just say x here instead. And also we were just using z as a stand-in for g of x. So I'll just replace that now. So yeah, that's the end of that proof. We started with the expected value of g of x and we got the Lotus identity over here. This one's not too hard to understand. Basically, when I take a function of these, I'm not actually changing the probability mass itself. I'm just changing the value that it was assigned. So it makes sense that we can just use that same probability mass, right? All right, so now let's do part B. Law of total expectation shouldn't be too hard either. This is my probability space here. So x is a discrete random variable. So what does it do? It partitions our sample space. So maybe this gets assigned to the value of x1. Maybe down here is x2. Maybe up here is x3, right? Now y is another discrete random variable, so it also partitions our sample space in some way. Maybe all of this region gets assigned to y equals 5. Maybe all of this region over here gets assigned to y equals 10. So now for this term right here, the expected value of x given y, let's think about what that is. So now we're given some value of y here. We restrict ourselves to where y is. Let's just say it's on this side. So now let's find the expected value of x in this region over here. So we know the definition of expected value. That's just going to be equal to all the values that x can take of x times the probability that x occurs, given that we're in this space y. So we know the definition of conditional probability at this point is just going to be equal to the probability that x equals x intersection y equals y over the probability that y is equal to this value. So now I'm taking all the values that x could take, given that y is true, so we're in this blue region. So I take the intersection right here, I divide it by the total probability mass of the blue part, I multiply it by the value of x. Then I do the same for down here. I take the probability mass, divide it by the blue part, multiply it by the value of x down here. And then I sum them up. So that'll give me the expected value of x given y. But now we have to take the expected value of this expected value right here. So when I take the expected value of this expression, well, all that means is now I'm summing up over all the total possible values of y. So not just this blue region over here, but this one over here. And I do the same thing that I did up here for this region. And then I weight the values that I get by their respective probability masses, and then I sum them up, obviously. So now you can pretty clearly see in this equation down here, I have a constant relative to the iterator in here, so I can just pull that inside, and then we'll get something like this, and then these are going to cancel right here, so I can delete those, basically. So when I do that, now I have a double sum out here, and I can just switch the order of them. You can switch the order of addition, obviously. And now what are we saying? Well, in the first iteration of our outer sum, we have some x value, so let's say it's this one up here. And we know that y partitions our entire sample space, so y must partition x as well. So in this case, it looks like this. And then in the inner sum, I'm going to iterate over all possible y values and take their intersection with our current x values. So in that case, it would look like this. I'm breaking it up into this part, and I'm breaking it up into this part, if you can see the black. Obviously, x is going to take the same value in both regions because we're holding it constant, so I can pull that outside. So again, for this term in here, we know the law of total probability at this point. Y partitions our sample space, so we know that when we sum up over all the possible values that y can take, intersection with our specific value of x here, well, we're just going to get back the probability that big X is equal to that little x. And again, you can see it up here, y partitions x up here. So we know that the probability of x is just going to be equal to the blue region plus the black region. So we replace this term right here with this new one, and you can see that this new term right here is just equal to the expected value of x.